Okay, so now we will return to Bayesian inference and talk about Bayesian posterior. We illustrated the Metropolis Hastings and the Metropolis samplers for drawing random samples from a given distribution. Now you know how that works, so let's substitute the target distribution f by the posterior density f theta given x. We will use the Metropolis sampler where the target distribution equals the posterior probability density of a parameter of interest. And let's see an example of this on investment model. So returns on different investments are usually not independent. And to reduce risk, for portfolios are sometimes selected so that returns of securities are negatively correlated. Let's suppose that there are 5 stocks which are tracked for 250 trading days. And on each day, the winner is selected based on the maximum return relative to the market. And let's propose a simple Bayesian investment model for stocks. Let xi denote the number of days that security I is the winner out of the 250 days. So we have 5 stocks, and they should be, on each day, there would be a winning stock. So xi records the number of days out of 250 that stock I wins. Suppose that historical data suggests that the odds of each security being a winner is 1/3 to 1 minus beta divided by 3 to 1 minus 2 beta divided by 3 to 1 beta 2 beta divided by 3 to, there should be columns over here, beta divided by 3. So this is the odds ratio for the five candidates. And here, beta is our unknown parameter, which we assume to have a prior distribution of the uniform distribution on the interval between 0 and 0.5. In other words, the prior density f beta of beta, because our parameter is not theta, it's called beta. So the prior density will be involving betas. It's going to be equal to 2 whenever beta is between 0 and 0.5, and it's going to be equal to 0 elsewhere. According to this model, given beta, x1, x2, all the way up to x5, will be multinomially distributed with probabilities of 1/3, 1 minus beta divided by 3, 1 minus 2 beta divided by 3, 2 beta divided by 3, and beta divided by 3, respectively. You can verify that these guys will sum up to be equal to 1. And the likelihood of beta given x1 to f5 is equal to fx given beta, which is equal to the multinomial probability. And this is equal to 250 factorial divided by x1 factorial times x2 factorial times x3 factorial times x4 factorial times x5 factorial times the product of pi's raised to the xi power. So because in this case, our prior is the uniform density, and that's a constant too, we know that the posterior distribution of beta given our observed x's is equal to f beta given x, and that's proportional to the likelihood, this guy, times the prior, which is 2. Because the prior is a constant, we can drop this, and the posterior density is hence proportional to the likelihood for multinomial. The problem is, even if we know the density, the posterior density for beta, we cannot directly draw betas from the posterior distribution. So what we will do is to use the Metropolis sampler to draw from f beta given x. In other words, to draw from the posterior density of beta given our observed data. This time, we will not use the normal proposal distribution. Instead, we will use a uniform proposal distribution where given beta t, the next y will be drawn from the uniform distribution between beta t minus w and beta t plus w. You can see that this is a uniform interval of bandwidth to W around beta t. It shares several similarities with the normal proposal. You can see that in this case, the proposal is symmetric, where gy given beta t is equal to gy beta t given y. Further, we can tune the bandwidth W to achieve a desired level of acceptance rate we like. For simplicity, we will just use W equals 0.25 here, but in practice, you might want to tune W and see when does it achieve a good acceptance rate. For this example, the acceptance probability will be given by the minimum of 1 and the posterior density ratio between these two. Okay, so instead of using some observed data from some data set, let us do a mini simulation study. Let's assume that we know the true beta, which is equal to 0.2, and we will generate the x's from the multinomial distribution with that probability vector, where the true parameter beta is given by 0.2. So here's the code for that. We first set beta equals 0.2, and that will be able to help us obtain the piece for each of the stocks. So the probability that the first stock wins is 1/3, and the second one wins is 1 minus beta divided by 3, etc. And the probability that the last one wins is beta divided by 3. Then we can use the sample function to draw samples of the winner for each day. We can do sample from 1 to 5, a sample of size 250, where the probability of each of the 1 through 5s is given by the piece vector, and we will do this with replacement. And then we will get a vector x's, which will be a length 250 vector where each entry is between 1 and 5, indicating who is the winner of that day. We will need to tabulate the x's in order to find out the number of days that each of the stocks win. So let's create a vector called win, which is the tabulation result of the x's, and that counts the number of days that the ith stock is the winner. So you can see that here, the first one won 94 times out of 250 days. Second one won 50 days, and the last one won 15 days. We'll do the Metropolis sampler with a total of 5,000 iterations. Like before, we create a vector to store our beta draws. And the first one, let's set it to some arbitrary value that is far from the true beta. So let's set beta 1 equals 0.4. We'll also create the K to increment the number of acceptances across the 5,000 iterations. And let's assume that in this case, we'll use the uniform with bandwidth to 0.25. Here's a function that evaluates the, here's a function that's proportional to the posterior density. We know that the posterior density actually is this guy, proportional to this guy over here. Our unknown parameter is beta, so we know that this part, 250 factorial divided by the 5 factorials, can actually be omitted when we're trying to calculate the ratio between these two guys, because this is a constant that does not involve beta. So we can just take this part. This is essentially what this function does. If we have a y value or a beta value that's outside of the support, so outside of the interval from 0 to 0.5, it will return 0, meaning that the density, posterior density should be 0. Otherwise, it will return p1 to the x1 power times p2 to the x2 power, etc., times p5 to the x5 power. So here's the code for the Metropolis sampler. I use the MH too much and has a tendency to call it the MH sampler, but it should be without the X, sorry. So we have set the initial value, so the first X to be equal to 0.4. And for each of the subsequent iterations, we first draw from the proposal. The proposal is a uniform distribution between beta, last beta minus W. and the last beta plus W. We'll then calculate the acceptance probability, which is the ratio between the function proportional to the posterior evaluated at y divided by that function evaluated at the last beta. If a uniform 0, 1 random number is less than or equal to p, we will accept this one and set the tth beta to be equal to y. We will also increment our k by 1. Otherwise, we will reject the sample, and our next beta will be equal to the last beta. Okay, so let's look at the results. Let's first plot the chain again. We'll plot the betas from the first iteration until the 5,000th iteration. You can see that this guy, which is the first guy that's really far away from 0.2, is actually our initial value of 0.4. But you can see that the chain converged really fast to a value that's quite close to 0.2. Yeah. The acceptance rate in this case is actually close to 15%. So in practice, what you might want to do is to make the bandwidth, the W, a little bit smaller so that it increases the acceptance rate to something around 0.3 or 0.4. In addition to looking at this, let's also look at the posterior mean. And in other words, you might remember this from last week. This is called the EAP. So the posterior mean of beta, which we denote by beta hat EAP, is an estimator for the true parameter beta based on the posterior distribution. We will toss away the first 2,500 iterations as burned in, and we will calculate the beta mean just using the last 2,500 iterations. And we can see that this is something close to 0.23. So it's not exactly 0.2, but it's not too far away. There's some random fluctuation in the sample we generate anyways. We can also create a empirical density plot for the posterior distribution of beta given x's. And if we do plot density of betas across, say, the 2501 to 5,000 iterations, you can see that this is a density which is centered somewhere around between 0.2 and 0.25. You can compare this to the density that we use as the prior distribution, which is the uniform between 0 and 0.5. That will be a flat line at y equals 2. So you can see that by using the data, we actually gained a lot more information about beta compared to the prior that we have used. So let's wrap up this week over here. And you can see that this week what we did is introducing the Metropolis Hastings sampler and the special case, the Metropolis sampler. And also we tried to plot the chains and to evaluate convergence. So does it get from a value far from the true value to somewhere that is close to the true value? Well, eyeballing this might not always be the best idea. So in addition to talking about the Gibbs sampler next week, we will also talk about some other methods that we can use to evaluate chain convergence. That is, help us decide how many iterations of burn-in do we need to toss away when we try to do posterior inferences.